Hello and welcome back to Data Science CastNet. In today's video, I thought we'd take a look at a couple of recent papers from the FAIR team at Meta, specifically on the topic of early fusion models. Models that are able to deal with multiple modalities, but that do so from the start in a very integrated way, as opposed to some of the more typical approaches of tacking on extra modalities right at the end of training. So to set the scene, let's quickly look at what I mean by that second thing. So this is the Gemma paper, and in this they take an existing text-only language model, the Gemma model, and an existing vision model. This is a SIGLIP, very similar to CLIP. It is a model that can map both images and text into some sort of shared space. Very, very useful for all sorts of image-related tasks. And so what we're doing in this formulation is we're saying, okay, we have a transformer model. It's used to seeing a sequence of tokens and producing more tokens, right? And typically those tokens are representing chunks of text. What we're going to do is we're going to learn some sort of projection, some sort of adapter to take this existing vision encoder and to take an image and map it to one or more tokens. And these tokens are going to be in the same sort of like token space or embedding space as the text tokens this model is used to dealing with. And then we can fine-tune various bits of this pipeline. But ultimately what we're ending up with is something that sees, okay, image token, image token, image token, image token, text token, text token, text token, text token, and then can generate future text tokens, right? So you could say, here's an image, here's a question about it, and then there's the answer, and I can train on that sort of data, learn these patterns within the sequence of tokens, what transformers are good at, and we end up with something that's really, really good. I mean, Gemma is surprisingly efficient and versatile model, nice and small and compact. So this is a recipe that kind of works, right? And we've seen this previously before this with Lava and GPT-4V, but like the open one that's named slightly confusingly, and a bunch of other models that do this. They take Blip or Clip and they mash that onto Llama or Mistral or some other existing LLM, and the two together they kind of fine-tune for a little bit to get this multimodal behavior. So this is fine, but it does kind of feel a little bit janky. Like, oh, we're trying to like project image stuff into this text token space or mess with something that's learned one domain and we're now adding another. And so you might think, and rightly so, I believe, surely we should be able to build in some of this multimodal support from the start rather than tacking it on at the end as kind of an afterthought. And so that's where Chameleon and the follow-up that we'll also look at MoMa, that's where these come in, saying, can we pre-train, like from the start, day zero, image support or support for other modalities like audio into some sort of foundation model that can do it all without having to have these like using different encoders and adapters and everything later. So that's the goal here, to build a so-called early fusion mixed modal model that can understand and generate images and text. So yeah, we're going to start with Chameleon. We'll see some of the amazing stuff that it does, also some of the like cons, the difficulties that they had, and then we'll look at the follow-on paper that shows how to train more efficient versions, and that also kind of gets around some of those effects. Okay, so we've got, let's see, introductions. People have been doing this. Okay, and here's the Chameleon architecture. So slightly confusing diagram because they try and pack lots of things into one diagram. But you can see here, for example, during the training, this here is our language model, except now it's multimodal. It's taking in image tokens and text tokens, and we'll talk about how those are generated. But it's still treating this like a generic language modeling task. I see this sequence of tokens, and for every token in, I'm predicting the next token. Right? So I have three text tokens, then the start of an image, then an image token and an image token, and it's predicting in each case what's the next token after that. Right? So that's our training objective. And we can fine-tune this for like instruction following and so on. And so when you like zoom out and look at the whole picture, that what they're saying is I can feed in a question, what can I bake with this? And I can feed in an image, and that's just going to be some additional tokens. And then I can have the model generate one token at a time, just like we do with normal language models. And it can generate, here is a recipe for banana bread. But it can also generate the start image token and a bunch of image tokens, and then the end image token. So this is like one at a time generating these tokens, and these tokens become some text but also become images. So this is a model that's not only capable of understanding images, but also of generating images. And they say it's trained end-to-end on 10 trillion tokens of interleaved mixed modal data, right? So one thing that's kind of interesting with this Chameleon paper specifically, like this is not like a small scale, oh, we just did a couple of experiments and called it good paper. This is we invested, 10 trillion tokens and a huge amount of compute and effort into training this thing, multiple versions of it, doing lots of ablations. They do release one, but I'll show you the one of the authors highlights, God will not forgive me for how we tortured this model to get it out. They released a version that doesn't have the image output capabilities. And so they've been, dropping hints maybe the community could undo whatever we did to make this model safe. Kind of entertaining. This, highly recommend giving Armin a follow. Lots of good commentary on the work that they're doing and the space as a whole. But anyway, so they did release some version of this model, albeit somewhat handicapped without all the capabilities. But I think reading between the lines, you can see this is more like proving the idea out for potentially future work, which we can maybe talk about what that might look like. Anyway, so there's a few questions that we want to answer when we're looking at this paper. One, how are they doing this tokenization bit? Like, how are we representing the images as tokens? Two, like, what does the data look like exactly? When they say this interleaved mixed modal data, like, what kind of data are they training it on? Three, like, does it work? Like, how good is it? Maybe four, are there any problems or difficulties with this approach? So let's skim through the paper and then we'll move on to the next one and try and answer those questions. What's the data that they're training on? Like exactly how are they tokenizing the image? What does this whole process look like? And how does it perform? So, okay, here's some sample interleaved image and text generation. So this is all generated from the model. Can you show me some cool, quirky looking birds and tell me about them? And so again, key here is that this model is not just like finding some images on the internet or anything. These are generated and so is the text. And it's able to do both of these just in the sequence, generate some text, generate an image, generate some text, generate an image. So that's kind of hinting at what they mean by interleaved data. Very, very cool that we have something with this capabilities. Okay, so we're going to have images and text as a series of discrete tokens. Tokenization. So this is how do we represent the images as text. They say we train a new image tokenizer based on this paper, which is Make a Scene. I wonder if I have it in my library. If not, it's not a worry. Okay, so I know from experience what Make a Scene does is it uses a technique that's, I think probably, well, the first ever DALL-E model used something called a vector quantized VAE, variational autoencoder, and it was a way of mapping an image to a sequence of tokens. And then this paper, Taming Transformers for High Resolution Image Synthesis, by some names you might recognize as being behind Stable Diffusion. Before they did that, they did this work on using something called VQ-GAN, so it's like also an autoencoder but with a GAN component, to turn an image into a sequence of discrete tokens. So you can see here I have an encoder that takes an image and it spits out some representation in like a latent space, and then there's a quantization step that maps these values to like discrete tokens. So token 1, token 42, token 3, token 3. And then when we have this codebook, we can decode this back into an image again. And we can also model a sequence of these tokens, these image tokens, using a transformer. So fantastic pivotal paper. Make a Scene, which is the one being referenced here, was a work from Meta. Did the same thing with a VQ-GAN, except that I believe they had some additional like perceptual loss so that the reconstructions were more faithful, especially for things like faces and text that really matter to people. But they say we encode a 512 by 512 image, so 512 pixels by 512 pixels, down to 1024 discrete tokens. So like code 1, code 27, code 82, out of a total codebook size of 8,000. Right, so you have now 8,000 possible tokens, and a sequence of 1,000 tokens represents a square image. They use only licensed images, and they upsample the percentage of images with faces. They keep talking about faces. You'll notice in this paper, none of the examples show a human face. It's very hard to find sample outputs anywhere that show this kind of capability. But again, this is still like early groundwork research on the one hand, but proved at a large enough scale that for anyone other than a big company like Meta, you'd be like, wow, how on earth are they not like then releasing this model into anything? But yeah, a few things like, oh, only training on square images. You can see this is still like just test phase, but still really cool. Okay, and then for the text, they have a somewhat standard tokenizer that has a vocab size of 65,536 minus the image codebook tokens. So was that like 57,000 tokens for the text tokens for the sentence pieces, and the rest for the image tokens. So yeah, that's how they represent their mixed interleaved data. When you see a sequence of tokens like this, text token, text token, text token, image token, image token, image token, that's the representation. Okay, so we know how they're representing images and text. Then let's look at the data. So they say we've got two separate stages. First stage, most of the training. Second stage, last 20%. We are going to use textual data sets, so like text only, 3 trillion tokens of just text, right? So this is just copy pasting data sets from Llama 2 and using this to like bulk out their pre-training data set with just like pure high quality text training. Then they also have, somewhat interestingly, specifically like paired text and images. So publicly available data sources, licensed data, these are image text pairs. So you can imagine like images with their captions or their alt text, very much like what you'd use to train a generative model like Stable Diffusion or Flux or whatever. And what they do is some of the time they have the image coming first and then the caption, right? So you imagine if you're seeing this one token at a time, you see a bunch of image tokens first and then the caption, you're learning to caption existing images. And then some of the time they flip that around and they have the text first and then the image. And so now I see a description of an image and then I'm learning to generate the image based on that description. So by doing this kind of switcheroo, they say, oh, we're hoping to give this model lots of capabilities for generating images based on text and lots of capabilities for describing an image with text based on the image. And then finally, they also just have this more general interleaved data, 400 billion tokens of interleaved text and images. You can imagine taking like a Wikipedia article. You have some text, then you have a figure, then you have some more text, then you have another figure, and then another figure, and then more text, just taking that whole thing as a sequence. So that's like the third component of their data. So quite handcrafted, but it's nice that we have a mix of text only, a mix of like text to image and image to text, and then some just general like this is images and text in whatever format we encountered them out in the web or in books and so on. Okay, so that's the data they're training on. So we've looked at the data, we've looked at the tokenization. Next, like, are there any tricky issues or problems? And one big one that comes up is stability. They say it was challenging to maintain stable training, especially as they scaled up. So they had issues with the architecture. They figure out like, oh, the softmax operation is problematic. And they go into this a lot, and I don't want to spend too much time dwelling on it, but it is kind of interesting to think about. We have, instead of just like, oh, I'm just modeling text, we have two very different domains, right? Images and text. Images, a very different modality, maybe different types of redundancy. You know, if you've got a big patch of sky, lots of similar tokens, different kinds of patterns within the data. So you can imagine that modeling them all with the same model might have some like quirks and issues. And specifically, one of the things that they call out is that you have this kind of like competition between learning to do well predicting image tokens and learning to do well predicting text tokens. These are kind of like different tasks. And so when they're training, you have the softmax operation that kind of like sums to one and is sort of assigning weight to different tokens or whatever. They talk about this kind of like competition of like, oh, trying to put more weight on the images, trying to put more weight on the text, and like these are kind of clashing with each other and growing weight norms or messing with the norms throughout the model. So one thing they do to fix this is they switch around the order of operations. So normally you would do you take your existing like embedding or whatever that's being fed through the model, your hidden state, and then you'd apply a norm to that, and then you'd feed that through the attention, and then you'd add that back to the hidden state. And the same thing, you'd apply a norm to that, you'd feed that through the feed-forward network, and then you'd add that back to the residual. So what they do in the Chameleon is they like switch around the norms so that instead I'm first feeding the hidden state through the attention, then I'm applying normalization, and then I'm adding it. So just a change of order of operations. There's a nice diagram in the follow-on paper that will show this nicely. Okay, so slight tweak of the order of operations there they find helps. They also messed with different like hyperparameters. I think they tried like weight decay and a couple of other tricks to try and get this in hand, but still struggled with these stability issues, although this architecture change really did help. Okay, so that's an interesting point. You can't just like copy and paste your llama training for this new tokenized image and text data regime. There's stability issues and quirks that come up. So this is them like kind of like exploring that ground for the first time and figuring out tricks to address that. Okay, so with all of that out the way, they do their training, comparing to Llama 1 and 2 and a bunch of other things. Yeah, a lot of GPU hours invested into these models, a lot of tokens passed through, huge amount of resources allocated to this, and very cool that we do get at least some hint of the model released openly, and some people are fine-tuning that and doing fun things. But yeah, very cool to see this big work, and it pays off. I think in the like performance and things, they do find that it's pretty it does pretty competitive. Yeah, so winning against these models quite a large percentage of the time. So very, very impressive model. Does really well at text tasks still. Does really well at like multimodal tasks. Yeah, and they fine tune it on like these kinds of tasks, like just like we do instruction tuning for a pre-trained language model. They do this for like, oh, here's an image, please give me a caption, or could you generate a story like this? It's able to do text-only things like poetry or code. It's also able to generate images just given a caption, or generate descriptions about an image. Yeah, so very, very cool model. That's Chameleon. And this is kind of like setting the stage for, I think, a lot of this early fusion style work. There have been other models before this. I don't want to say like, oh, this is the first one. Fuyu from Adept is an example of another model that just took the same approach, just map everything to tokens and then train a single decoder-only model on that. There's other closed source options, obviously, that are working on early fusion, truly multimodal models. You've seen that around for a while, but it's nice to see some good open work being done on this. Okay, so now in the second half of this video, we're going to look at a follow-on, which is saying, okay, Chameleon was cool, like it proved the concept. We can train from the start on interleaved like text and images. Can we do it more efficiently, right? Are there ways we can speed up training for the same performance? Are there tricks we can do? And so we have MoMa, and this is efficient early fusion pre-training with mixture of modality-aware experts. So we'll go into all of the different types of mixtures and sparsity and so on. Okay, so skimming the abstract, they say this processes images and text in arbitrary sequences, just like Chameleon. Our empirical results reveal pre-training efficiency gains through this technique that they're going to introduce. Training on 1 trillion tokens, MoMa does 3.7 times overall flops savings compared to the baseline, which is Chameleon. Right, so improving over this previous thing for the same like budget of tokens and parameters or flops, we're getting a big boost 3 or 4 times or 2 or 3 times in performance compared to that baseline using these new techniques. So let's dig in and see what are the changes to Chameleon, like what are the different pieces, and also keeping in mind some of the challenges that Chameleon had. How did these maybe address those? Okay, so they're going to suggest several different things. One is modality-aware sparsity, right? So we'll look at how are we doing the sparsity. And they're doing it in a few different ways. So they talk about mixture of experts, right? So this is having, instead of all of the tokens flowing through all of the weights of the model, we instead have different sets of weights that are activated for different tokens. Mixture of experts, and they're going to investigate the effects of that. And also they're going to do this in a modality-aware way. So having some experts that only toggle on for image tokens and some for text tokens. And then they're also going to have mixture of depths. And so this is another concept, mixture of depths, dynamically allocating compute in transformer-based language models is a good reference for this, where instead of going through all the layers, all tokens going through all layers, we have an option here right at the start of each transformer block that decides whether or not a given token can skip that transformer block. And so rather than all tokens using all blocks, some tokens will skip certain layers in the transformer. another way of just reducing the total amount of compute and saying that, oh, maybe not all weights are used for all tokens. Instead, we're able to have more weights, but only some of them are turned on. So this kind of sparsity is going to hopefully give a performance boost. Okay, so they have these multiple dimensions. We're splitting along different experts, right, for different tokens within a layer, and then we're also skipping certain layers with this mixture of depths. Yeah, we're going to talk about how exactly they do that and what the results are. One thing that they find is that the mixture of experts and the modality-aware mixture of experts stuff, that's like a general improvement, right? That's always better. It's more efficient, and it matches the performance of the comparison. Adding the mixture of depths, where you're skipping some layers, it does boost the savings further in terms of like computational efficiency, but they noticed that the performance does drop, right? There's some sensitivity to the accuracy of like, oh, should I be skipping or not? If that's not perfect, it kind of compromises the performance a little bit. So I think the end result of this paper is saying, hey, the mixture of expert stuff definitely works. We should definitely be doing that. The mixture of depths like possibly works, possibly gives some efficiency gains, but also makes it trickier to do inference, makes it trickier to balance loads, and like might compromise performance a bit. So maybe that's not so much of a strong recommendation, but still cool that they explore it. Okay, so let's have a look at what the setup is here. So this is exactly like Chameleon and before. We have text and image inputs. Both of these get tokenized. They don't change anything. I think they don't even change the pre-training data mix from Chameleon. So we're sticking with that baseline, training slightly smaller models. And then we're just learning to model these sequences. So text token, beginning of image, image token, image token, image token. The difference is that these transformer blocks, instead of just being a normal dense transformer block, they have this multiple steps where we have self-attention, then modality untying. This is splitting the image tokens go one way, the text tokens go another way. And then within the text tokens, there's multiple possible experts, right? And so the expert choice router is choosing which expert sees which token. And then after being processed by one of those experts, those tokens are then combined with the ones that have been processed on the image side, stacked back together into the original sequence, and then they flow on through the network. So we have this division between image and text tokens, right? Some parts of the feed-forward network processing image, some processing text, and then we also have within those the mixture of experts, like multiple experts for each modality. So when we're looking at the different like configurations, we'll see that they have the number of experts per images and for text, and being able to sort of dynamically say, what if we have more experts for text versus images? Those are kind of interesting additional experiments. Again, going back to the like concept of these are two different domains, maybe different types of redundancy, different types of compute needed. So it might make sense to allocate more computation to images or more computation to text, and we'll see how that plays out. In terms of how the routing happens, they have this expert choice routing. If you're familiar with mixture of experts, the vanilla or like typical way to do this is we have, for each token we're going to do this process. We have a token coming in, we feed it through like a little router, which is usually just a single layer, and this is going to output scores to say, oh, whichever like output is highest, that corresponds to one of the experts, right? So I feed this token through, I see which output is highest. Oh, okay, output 2, so I'm going to feed this through expert 2, and then I'm going to take that. And then the next token comes along, I feed it through that same router. Oh, this time the first output is highest, so I'm going to feed it through the first expert. So that's your usual mixture of experts approach. One issue with that is that you can end up with kind of imbalance, right? Where this router learns, oh, I just always route to experts 1 and 2 because they do better. And so then these other experts get like underutilized. So they're mostly just like wasted. So you have like imbalance in terms of where the computer's being done. You've got all these weights that aren't being used, or it's just inefficient. And so this expert choice mixture of experts that was maybe proposed, I think, in like 2022. Instead, what they do is they have for every expert has its own router. And those are going to look at all of the tokens, and then we're going to choose the top K tokens that activate this router are going to go to this expert. The top K tokens that activate this one are going to go to this expert. And what this means is that we can have like some more dials we can control to say, I'm going to ensure that every expert sees, K tokens, right? So rather than having it just be, oh, if the router always says go to the first expert, that expert's going to see all the tokens, the others aren't going to see any. With this expert's choice scenario, we can set it up so that each expert sees some number of tokens. And that helps us like control to say, oh, let's make sure all the experts are getting used. And if we want more experts to process each token, we can tweak that parameter during sampling or whatever. It just gives you a bit more control and helps balance the load across the different experts more effectively. So anyway, that's the side note on the expert choice mixture of experts. And that's what they're using here with this EC symbol in the diagram, is just saying, oh, we have this situation where each of these experts has a corresponding router. It's being run over all the tokens, and then the top K tokens from that, which is something we can configure, are being sent to the corresponding expert. And there's some subtleties like during inference, you can't just look at all the tokens because you want to be doing one thing at a time. So you can like replace these routers with others. A whole big like rabbit hole that I'm not going to go down. But just know it's a pretty good approach for dividing the work between multiple different experts, these different feed-forward blocks, I guess, within the single transformer block. Okay, so a lot of waffle out the way. Now we know what the architecture looks like. We know what the data looks like from the previous one. So we can skim through and take a look at how this actually works and what they find. Okay, so here's a good diagram of the architecture. And you'll see self-attention and then the norm, feed forward and then the norm. This is that like architectural change where often in transformers you'll have the norm first and then the module. So yeah, nice to see that in pictorial form. Mixture of depths, we looked at the paper, just skipping certain layers. One other interesting dynamic that they talk about is when we want to create a bunch of experts, one way to do that is just to randomly initialize them all and start training. But then there's some potential issues with that because at the beginning, all of them are random, right? Everything's randomly initialized, the performance is terrible. So you're trying to learn the weights for all of those experts, but you're also trying to learn the routing. But at the beginning, you're just routing to like terrible options, right? And so this can throw off the proceedings a little bit. And so what they find, and this is very interesting, and I think maybe speaks to some techniques that other companies are using, is that starting with a single expert, or a single expert per modality in this case, training for a little bit, right, until that's at least like a reasonable starting point, and then duplicating those weights for however many experts you want, and letting them start to diverge as you continue to train. That's a much better approach than just starting from random. And so, this is something people have been like aware that other players must be doing. So for example, in the Mixed-Modal model, which is like Mistral's, mixture of experts offering, each expert, like there's a lot of correlation between them, and also correlation between those experts and the weights of the dense like base Mistral model. And so everyone's like, oh, they must be doing some sort of upcycling to take your dense base model, that's like 7B, and turn it into your 8 expert, 8 by 7B mixture of experts model. And I think this is a good hint that, oh, yeah, that is possible. But also, interestingly, like you should do this quite early on. So you don't want to train all the experts from the start, but you also don't want to train a single one for too long and then upcycle it. They say, and we'll see this in the results section, training for like 10,000 steps, I think it is. There's like some sort of sweet spot where, okay, cool, I kind of like have boosted my performance by not starting from scratch, but I haven't trained that expert too much to the point where it's like hyper specialized and it doesn't make a good base for other experts. So yeah, that's like a nice, it's somewhat tangential to this paper, but it's very, very useful and practical for anyone doing any mixture of expert stuff. Cool. Okay, so they're going to do some experiments at 1.4 billion parameter scale on the Chameleon dataset and preprocessing. And yeah, we're going to start to get to these performances here. So on the x-axis is a measure of like compute, and on the y-axis is the training loss. And so these blue lines are the dense version. So this is like the Chameleon baseline. And then as we go from here, lower loss is better. These are going to be their proposed changes, right? So MOE 8x, this is just a mixture of 8 experts, no splitting between the modalities. MOE 1T, 1I is one text expert and one image expert. So this is saying no like proper mixture of experts, but we'll put the image tokens through a separate feed forward head to the text tokens. And then MOE4T4I is like, okay, now I have 8 experts, 4 of them process image tokens, 4 of them process text tokens. And you can see these configurations give a better performance per flop than the base model. Now, it's worth highlighting here, and keep this in mind throughout this paper. They talk about like compute matched variations. This is not exactly apples to apples, because the dense baseline is 1.4 billion parameters, but the sparse versions, it's like they might have a lot more parameters, even though only a subset are activated. So I think if we scroll down here, you'll see the dense version, 1.4 billion parameters. The mixture of experts, 7 billion parameters. The mixture of depths, 2.3 billion parameters. Mixture of depths and experts, 12 billion parameters. So all of these theoretically use the same amount of computation, right? Because not all of the experts are being activated for every token. But the mixture of experts has a lot more parameters that it can use to store different facts, or use more tactically. And for us GPU poors, like having to keep all of those weights in RAM is not free, right? So there is a trade-off of having more experts, more parameters to store, even though not all of them are activated every time, especially if you're like doing inference yourself, batch size of 1 on a small GPU. Suddenly the number of parameters actually matters more than the compute, and it might be better to have a dense model, even though the compute matched sparse version is in theory the same, because it has all these extra parameters that you have to keep track of. It can be a little bit worse. So that's just a big caveat, is to say when they say compute matched, they mean like compute in terms of operations per forward pass or whatever. But those sparse versions might have a lot more parameters, and so it's not exactly apples to apples, but still, it's apples to apples in the thing that they care about, which is how much compute that we spend pre-training and doing inference, right? And so these improvements that they make, these different configurations, they show quite a significant speed up for a given like flops per token value. Pretty good results in terms of speed up. And then we can check the performance. So training loss, a good measure of like downstream performance, or like how well it's learning the patterns. Again, here, so starting on the green, 1 text, 1 image, going down to 4 text, 4 images, or 1 text, 1 image, or some mixture of depths versions. And it's interesting to note, so like as you're looking at these charts, they also report the text only training loss and the image only training loss. And you'll see like in some of these cases, so let's look at here. Comparing 4 text and 4 image versus 6 text and 2 image versus 7 text and 1 image. On the image modality, 4 text, 4 image is the best, right? Because it's got 4 experts allocated to the image tokens. That kind of makes sense. When you drop down to only 2 experts allocated to image tokens and 6 for text, it's a little drop in performance, but not much. But when you drop down to only a single expert for images and 7 for text, the performance drops quite a bit further, right? So you're kind of sacrificing a little bit going down from 4 to 2 and a lot going down from 2 to 1. On the text training, using 7 text experts versus 6 text experts, almost identical. Using 4 text experts, it does drop down a little bit, but not a huge amount. And so there's kind of this like trade-off here of saying, okay, I could have even like 4 text and 4 image, but it seems like maybe I want to do 6 text and 2 image, which gives me a little bit of a drop on the image side, but a decent improvement on the text side, which maybe I care about slightly more. So this is what I meant when I said having this like separate experts per modality and being able to tune the number of experts. It's really cool because it starts to give you these insights and these knobs that you can tweak to say, hey, I want a really good model, but I especially care about its performance on text and code. And it would be nice if it did images too. It's like, oh, great. Well, now you can say, when I'm designing this model, maybe I'll allocate 8 of my experts to text and 4 to images, right? You can kind of like tweak the ratios there and choose how much of your parameters are going to be focused on those specific modalities. So text modality may benefit more from a larger number of experts. That's an interesting takeaway, and it's nice to know for downstream work that that's something you could maybe design in. Upcycling, so this is their initializing the experts bit. They find that initializing from 10,000 steps is this purple line here. This does better generally overall. You can initialize from 20,000 steps, and then it takes a little bit longer, but it still gets pretty good. Whereas starting from the no initialization at all, just training all of the experts from scratch from the start. Slightly worse performance. So that's their recommendation, is train a single expert for each modality for about 10,000 steps, and that might change depending on how many tokens training you're doing in total, but something quite low relative to the total number of training steps, and then duplicate that and train further. Yeah, so interesting little side bit there. Okay, they do some throughput analysis to go into the performance things that I talked about, where the sparse models don't necessarily give you like this perfect performance boost. One thing that they talk about here is this idea of like load balancing. If you have a model that has, say, 4 text experts and 4 image experts, and then you go through a batch of data that's all text, those image experts are sitting there and they're not being trained, but maybe they're taking up space on your GPU or whatever, and that's not ideal, right? And if you're doing this distributed, where you have multiple GPUs, and some of those GPUs are handling the text experts and some are handling the image experts, and then you process some data that has no images, well, those GPUs are sitting idle, right? And that's going to hurt your efficiency in terms of pre-training. And so they do various bits of work to address that. They have making sure that the data mix is kind of even, and then also, tweaking like how much of those different modalities is in the training to kind of balance out across those different experts and across the GPUs and so on. And then they talk about, for inference as well, there is some throughput loss from having to do the routing decisions and so on with the mixture of star, but it kind of still pays for itself in terms of performance. Okay, so I think that's that. The stats, kind of fun to browse through if you're interested to see which cases, like, having more text experts or having a balance, like, does that affect whether it does better on image benchmarks versus text benchmarks? But in general, their approaches that they're describing here are improvements over the baseline, and that's the main takeaway. Limitations, I mean, they do this pretty small. They talk about the imbalance that might still occur during training. But yeah, this is a really nice like follow-on to Chameleon. I think if you start to extrapolate where this is going, Meta, this is a company that released very successful text-only models, and they started with Llama 1, Llama 2 scaled up, Llama 3 scaled up, they further pre-trained Llama 3.1, but these are still like the tried and tested text-only transformer approach, right? And Llama 3.1, maybe there's some multimodality in there, but if it is, it's the like late edition style multimodality. Whereas you can see in parallel to developing Llama 3, they're also doing these experiments on Chameleon, on MoMa, starting to build up this skill set of like, if we were to train early fusion multimodal from the start models, what would that look like? How would it scale? They tested at 34 billion parameter scale with Chameleon. They find that it does really well, but there's stability issues. They're starting to figure that out, and also now they're doing this mixture of expert stuff. And remember, like, rotating the images and the text separately, that kind of also helps solve this issue of the two modalities fighting to try and like compete in terms of loss for images versus loss for text. Having them separate in different experts is like a nice way to address that. Working on efficiency for training, you can see that this is building a really nice baseline to say maybe Llama 4 or some other model is going to be a very powerful, properly, truly multimodal from the start model, and they've done the groundwork. So yeah, nice to see those couple of papers, I think. I hope you found that interesting. If you have questions, feel free to leave them down below. I'll try and look through the comments. Otherwise, we'll see you in the next video.